Hello everyone. First I would like to thank the organizers for the opportunity to give a talk at this very nice meeting. I would like to talk about the derivation of the Landau-Pekar equations in the strong coupling limit, and the talk is based on joint work with David Mitruskas, Simone Rademacher, Benjamin Schlein, and Robert Seidinger, and can be found on the archive. The outline of the talk is as follows. First, I would like to give a small motivation and explain the models we are looking at, namely the Fröhlich model and the Landau-Pekar equations. Afterwards, I would like to present our results and, if time permits, give a sketch of the proof. So let's start with the motivation. In this talk, we are interested in the behavior of an electron in an ionic crystal. And if we look at the right picture, we see that the electron repels the negative ions and attracts the positive ions. And this, so to say, leads to a polarization of the crystal and creates a potential which then acts back on the electron. And if the electron now moves in the crystal, the polarization follows and surrounds it and modifies its physical properties like the effective mass. And for situations when the extension of the electron is much larger than the lattice spacing, Fröhlich derived a model in 1937 which treats the crystal as a continuous medium and describes the polarization as the excitations of a quantum field, and these excitations are called phonons. But when the coupling between the electron and this quantum field is strong, it is expected that, so to say, the quantum field behaves classically, and for these situations, Landau and Pekar proposed a set of equations which describe the interaction between the electron and a classical phonon field. And maybe I should say that this I have forgotten. This composite of this electron and this polarization of the crystal are called the polaron. And the Fröhlich model is the following. So it's defined on the Hilbert space, which is the tensor product of L2R3, which describes the electron, and the bosonic Fock space over L2R3, which describes the phonons. A state in this Hilbert, space evolves according to the Schrödinger equation with the following Hamiltonian. And if we look at the Hamiltonian, we see that we have a kinetic part of the electron, and then we have the field energy. And since this model describes the optical branch of the phonons, the dispersion relation is approximately constant. That's why the field energy is just given by the number operator. And then here we have an interaction potential, or we have an interaction between the electron and the phonon field. And the interaction has this form factor and has annihilation and creation operators, which are defined by the usual definitions and satisfy the usual canonical commutation relations. In principle, one must be a bit careful because this function gxk is not in L2, but one can define, so to say, the time evolution via the associated quadratic form. For the following, so if we look at the Hamiltonian again, we see that we have here a parameter alpha, which models the coupling strength between the electron and the phonon. And for the following, it will be convenient to go to strong coupling units. And in order to do this, we scale the position of the electron, the variable k, and then we redefine this annihilation and creation operators. And if we do this in this way, this square root of alpha disappears in front of the interaction term, but we get an overall factor of alpha minus 2 in front of the Hamiltonian. And we also get a factor of alpha minus 2 in the canonical commutation relations. And in order to get rid of this factor, it's convenient also to rescale time. And then we are ending up with the following model. And I would like to stress that, so to say, in our new time scales, times of order alpha squared corresponds to times of order 1 in the old units. So if we look at the model, we see that we now only have this scaling parameter appearing in the canonical commutation relations. And this suggests that for large values of alpha, so to say, the quantum field behaves classically and can be approximated by a classical field. And a central role, if one wants to study the classical behavior of quantum fields, is played by coherent states, and in this context also by Pekar product states. And coherent states can be defined by acting with a while operator on the vacuum, and the while operator is a unitary operator which satisfies these nice shift properties. And the Pekar product states are then a product state of an electron state with a coherent state, which is given by the action of the while operator on the vacuum. And the importance of coherent states come from the fact that they are eigenstates of the annihilation operator, and if they have a large occupation, if they have a large phonon number, then they are almost eigenstates of the creation operator. And these relations can be directly obtained from the shift property of the while operators, namely, one can just add here a W star, and then one can use the shift property, and if the annihilation operator acts on the vacuum, this term disappears, and then we see that it's an eigenstate. And if we do the same for the creation operator does not disappear, but since we have the scaled canonical commutation relations, the quantum fluctuations are of order 1 over alpha. Okay, so we can take, for example, this Pekar product states and compute the expectation value of the energy. So if we look at our Hamiltonian again, then we can just compute the expectation value, and with this property we just obtain an expression which only depends on this electron wave function and the state of the coherent state, and the state of the coherent state. And this right-hand side is also referred as the Pekar energy function. So we see by using Pekar product states, we can obtain an upper bound on the ground state energy of the many-body system, but that actually there's also the corresponding lower bound that's much harder to show. And this was done by Donska and Baladan in 83, and later by Lieb and Thomas in 97 by more analytical tools. And more recently, by Frank and Seilinger, the next order correction to the ground state energy was shown in case of a confined polaron. In addition to this question, one could also ask the dynamic question. So if we start with a Pekar product state, is the structure preserved during the time evolution? And if this is the case, it is expected that also there the quantum field behaves classically, and the coherent state can be described by the Landau-Pekar equations. And the Landau-Pekar equations are this set of equations, and if we look at it, we see that the electron wave function satisfies a Schrödinger equation where we have a kinetic term and a potential, which is the same potential from the previous slide. But if we now look at the equation, we see that the potential has a mode function which satisfies an equation by itself. And the first term in this equation ensures that the potential would behave if it would not couple to the electron like a harmonic oscillator. And the second part of this equation, so to say, couples to the density of the electron. So we see that, so to say, the phonon potential that the electron couples to the phonon potential, and it has the electron as a source term. So this is a set of nonlinear equations. The well-postedness for these equations were shown by Frank and Young. And if we look at the equations again, we also see that we have here this parameter alpha. This again corresponds to the coupling between the electron and the phonon field. And since we're in strong coupling units, it appears here in the equation. And if we look at the equation, we see that for large values of alpha, we have a separation of scale because the mean momentum of the electron is of order 1, while the variation of the phonon field happens, or while the variation of the phonon field is of order alpha minus 2. So this separation of scale, will play an important role later, but now I would like to state our results. And just as a reminder, we would like to show a result of the following form. So we start with a Pekar product state and let it evolve in time. And then we want to show that it approximately preserves its structure and that psi t and phi t are described by the Landau-Pekar equations. And our first result is about reduced density matrices. And I start with an initial value phi naught, which is such that the corresponding Hamiltonian h phi naught, and this Hamiltonian h phi is this Hamiltonian from the previous slide, admits a unique positive ground state. And then we take as initial state for the electron that the electron is in this ground state. For the many-body state, we then consider a Pekar product state where we also have the electron in the ground state, and phi naught is exactly the phi naught, which satisfies the same initial conditions as the solution of the Landau-Pekar equations. Next, I have to define the one-particle reduced density matrix of the electrons. And this can be just done by looking at the projector of the many-body state and then tracing out the Fock space. And the one-particle reduced density matrix of the phonons can be defined by its integral curve. And then our theorem is saying the following, that the one-particle reduced density matrix is for until certain times of order alpha squared, approximated by the projector onto this function psi t. And the one-particle reduced density matrix of the phonons is approximated by the projector onto the function phi t of the phonon field. So this result is actually a corollary of a stronger result. Namely, one can also approximate the many-body state in norm. And in a similar way, or similarly, as one knows it from the derivation of the Hartley equation, one has to take quantum fluctuations into account in order to obtain a norm approximation. So to get the norm approximation, I now define a Bogoliubov dynamics, which is defined on Fock space and generated by the number operator in a quadratic Hamiltonian. And with this Bogoliubov dynamics, one then can show the following, namely, we start with the same initial conditions as before, and we allow that we are not exactly in a coherent state, but we can have small deviations. And then we can approximate the time-evolved state by a state which is given by the Bogoliubov dynamics and the solution of the Landau-Pekar equations. And this also holds until certain times of order alpha squared. And the important thing is that the Bogoliubov dynamics is also completely determined by the Landau-Pekar equations. And the explicit form is maybe not so important for the moment, but it's good to keep in mind that the Bogoliubov dynamics, so to say, describes the correlations between the phonons. So one could ask if one has to include these quantum fluctuations only because of technical reasons, and that this is not the case can be seen from this result. So if we now look again at the Pekar product state, and then we replace the quantum, the Bogoliubov dynamics just by the vacuum again. So we want to approximate this state by a time-evolved Pekar product state. Then one can find times of order alpha squared such that these two states have a deviation of order 1. So in conclusion, one can say that the Landau-Pekar equations approximate well the time evolution of the one-particle reduced density matrices. However, for a norm approximation, quantum fluctuations has to be taken into account. And what is also important is, since this parameter alpha squares enters into the Landau-Pekar equations, non-trivial variations of the phonon field happens on time of order alpha squared. So it's really important to obtain a result of order alpha squared to show that also the phonons that are created during the time evolution show classical behavior. And this condition that the electron wave function at time 0 must be in the ground state of this Hamiltonian h phi naught is crucial, and I hope I will find later with time to motivate this more. But first, I would like to make a comparison with the literature. So the rigorous derivation of the Landau-Pekar equations were initiated in a work of Frank and Schlein, 2013, and there they derived a result for times of order alpha. And for these times, they could show that the time evolution of a Pekar product state is approximated by a Pekar product state, but here the phonon field does not change in time, and the electron, so to say, feels a potential, which is also the initial potential of the phonon field. And this is possible on this time scales, since the variation of the phonon field is so slow, that it just appears as an external potential. Later, Frank and Gang considered the Landau-Pekar equations and derived the true evolution by a Pekar product state, and could in this way improve the rate of convergence. Afterwards, Griesemer derived a result for a very special state, namely he considered the minimizer of the Pekar energy, which I had on the second slide, and looked at the corresponding Pekar product state. And one has to keep in mind that this minimizer of the Pekar energy is a stationary state of the Landau-Pekar equations. So in a sense, it stays constant, but only creates a phase during the time evolution. And then by a oscillatory phase argument, which also became very important for the later derivations, he could extend the time scales to order alpha squared, and could show, so to say, that the evolution of the special state is just given by a phase factor. And it's important to keep in mind that this is for times small compared to alpha squared. Then Simone Rademacher, Benjamin Schlein, Robert Zaringer, and myself could extend this result to the more general states I've presented before. And this was possible by means of an adiabatic theorem. Later, Mitruskas improved the result of Griesemer by including a Bogoliubov Hamiltonian. So to say, by including additional correlations, he could show that he could approximate the special state for arbitrary times of order alpha squared. And the latest result is the result I just presented. And this only holds for certain times of order alpha squared. And why this is the case, and why we have to look at the special initial conditions, I would like to motivate now. So the ingredients, so in order to estimate this difference in norm, one uses the Duhamel formula, and to get on the right time scales, one then has to use the oscillatory behavior of an integral. And in order to do this, one has to show that this Hamiltonian h phi t, which appeared before, has a spectral gap of order 1. And this can be ensured very easily, namely with our initial conditions. We could view the spectrum at time 0 to be at the of the following form. So we have an essential spectrum above 0, and then we have a lowest eigenvalue, and we have a spectral gap of order 1. And by means of the Landau-Pekar equations, we can write the Hamiltonian at later times as the Hamiltonian at time 0 minus a perturbation. And the important point is that we have this factor here of alpha to minus 2 in the perturbation, because then one can use the min-max principle to show that the lowest eigenvalue stays underneath a line which has slope of order 1 over alpha squared, and the rest of the spectrum stays above this line. With this spectral gap, we could prove an adiabatic theorem, so Simone Rademacher, Benjamin Stein, Robert Zahlinger, and myself, which states the following. So if we start with our initial conditions, and the electron is, so to say, trapped in this phonon potential, and then if we let the system evolve in time, the phonon potential changes. But since the speed of the electron is so much faster than the change of the phonon field, the electron immediately adjusts and then goes into the ground state of this time-evolved Hamiltonian h phi t. And this ground state is described, so this ground state is named psi phi t, and the theorem says the following, namely, for times until the spectral gap remains open, the solution of the Landau-Pekar equation for the electron can be approximated by the ground state of this Hamiltonian h phi t. Okay, now maybe I have a look at the time. It's probably already over.
I think you still have some minutes.
Okay, that's very good, because then I would like to try to motivate where the oscillatory phase comes in, which is not so easy in a very short time. But so we want to show that this difference is small. And as a first step, we replace the solution of the Landau-Pekar equations by means of the adiabatic theorem by this ground state of this Hamiltonian h phi t. And then we can just look at this non-difference and rewrite it. Then we can put the phase on the vector on the left-hand side, and we can also multiply it with the adjoint of the y operator. And then we can write the norm difference in the following form. And here we see that we want, so this vector is often also called fluctuation vector. And what it does is, so we have our Pekar product state, we let it evolve in time, and then we annihilate the coherent state of phonons. So what remains in the radiation field are, so to say, the excitations above this coherent state. And then we also have this time-evolved electron state, but which here also features some correlations. And now we want to show that, so to say, the electron state is close to this ground state, and that these fluctuations in the phonon field are described by the Broglie-Wolff dynamics. And in order to do this, one uses Duhamel's formula, and then one gets an integral. And I haven't written it out, but if one computes the time derivative, one sees that this integral is of order alpha minus 1, which also explains a bit why the first results were for times of order alpha minus 1. But the interesting fact is one can now compute the time derivative of this vector psi t. And if one looks at this integral, then one can insert the projector onto this ground state vector of this Hamiltonian psi phi t, and this contribution vanishes because this is, so to say, kind of the mean field contribution which get cancelled by the effective equations. However, then there are terms where we have the projector onto the orthogonal complement of this ground state vector psi phi t. And the interesting point is now, since we have the spectral gap here, and we are projecting away from the ground state, we know that this term is of order 1. And if one reminds one about the scaled canonical commutation relations, one can think of this quantum field to be of order alpha minus 1, and of the number operator to be of order alpha minus 2. And the interesting point is, if one now, so to say, looks at all the different quantities in this integral, the time derivative is of order alpha minus 2. So one, in a sense, has a phase which, with some correction of lower order, is of order 1, and which is relatively fast, to the change of the other quantities. And this allows then to write this left-hand side here, which is of order 1, as the resolvent times some time derivative minus the quantum field minus the number operator acting on this function psi s. And so here one can see this quantity is of order 1, but if we then do an integration by parts and all other quantities change, the change of all other quantities is of order alpha minus 2, we can use this, so to say, to get an additional effect of alpha minus 1. And in order then to get on the right time scales, one has to do this partial integration or this argument at least twice. And for this to be possible to perform it twice, it's important that one implements, so to say, the quantum fluctuations by the Rublev dynamics. Okay, so I shortly just want to mention that the importance of an adiabatic theorem for the derivation of the Landau-Pekar equations were already stressed in a paper by Frank and Gang, in which they also prove an adiabatic theorem for the one-dimensional Landau-Pekar equations. Okay, so I think my time is over, and I would like to thank you for that.